Hi, welcome back to this channel. We are going to start with chapter 6. These are the learning objectives that we are going to cover in this video. Tutorial question number 1. We are going to ask to state two characteristics for a dynamic equilibrium. So, enclosed system, basically this is not the characteristic, but this is considered like the requirement. Next, reaction is still progressing. No further changes in the amount of reactant and product, or the concentration keep constant. Okay, this is very general characteristic that can very easier to differentiate dynamic equilibrium and irreversible reaction. This is also the characteristic that we always mention. Rate of forward reaction equal to rate of reverse reaction. So due to this, we know that a substance will react to give product, and then at the same time, the reverse reaction also will give the reactant. So basically, this is just an explanation. The next, equilibrium could be reached in either way. So same case with the third one, can move forward and also reverse. So this is also considered as explanation. Let's proceed to question number 2. Define the homogeneous equilibrium and also heterogeneous. So homogeneous equilibrium is considered an equilibrium that involves reactant and product in a single phase. While for the heterogeneous equilibrium, it can have more than one phase. Let's continue with 2b. Determine whether the following reactions are homogeneous or heterogeneous. So basically, 2, 3, 4, 5, and 6 are heterogeneous because there is more than one phase. For example, we have solid, gas, solid, gas, solid, liquid, aqueous, solid, solid, liquid. Okay, only P1 is homogeneous reaction because all the reactants are in gas as well as the products. Tutorial question 1c need us to write the equilibrium law in terms of Kc and also Kp. So do remind that the equilibrium law only applicable for weak electrolyte or the dilute solution. So and then do always keep in mind that pure solid, pure liquid, and also solvent will not appear in the expression. For the term square bracket A is referred to concentration, while PA is referred to the pressure. So at constant temperature, the equilibrium constant does not change. This is the answer for tutorial question number 2c. Because of the first equation consists of gaseous substance in the system, means that we are able to write both Kc and Kp expression. While for the question number C2, the reactants are solid, so solid will not appear in the Kc expression. So by right, it is over 1. But anything that's over 1 will equal to, let's say, will equal to the similar expression. For example, 2 over 1 is equal to 2. So in this case, this student does not show over 1 in the expression, also okay, no problem. Question number 3, again, all these have consist of gas and also solid. That's why we only will see carbon dioxide over carbon monoxide. For question number 4, similar case happened as question number 2. solid and liquid are not exist in the expression. So that's why at this question number 4, only H2O gas appear in Kc and Kp expression. That for the second last one, we have aqueous and solid, but aqueous also will not exist in Kp expression. So that's why there is no Kp expression in this case, only have Kc expression. So question number 6 also similar with question number 4 and 2, which they consist of solid and also liquid. So only hydrogen gas appear in the Kc and Kp expression. So simple to say, any substance with the physical state aqueous and also gas will be appear in Kc expression, while for Kp expression only those are in the gas phase. Proceed to tutorial question number 4. Some nitrogen and hydrogen are placed in an empty 5-liter container at 500 degrees Celsius when equilibrium is established. Okay, so means that at equilibrium, the number of mole is 3.01 mole for nitrogen, 2.1 mole for hydrogen, and 0.565 mole of NH3. Calculate the Kc for the reaction at 500 degrees Celsius. So again, the question is asked for Kc, so means at equilibrium, constant. So here the C again is stand for concentration, so we cannot directly write the Kc expression first. We have to convert all this number of mole in unit of concentration. So 3.01 mole divided by 5, so we will get 0.602 molar for nitrogen, and hydrogen 0.42, while ammonia is 0.113 mole per decimeter cube. Okay. Then we are going to write the Kc expression, which is product over reactant. Don't forget the power over here, and then substitute the value in, press the calculator, and you will get 0.826. Let's continue with tutorial question number 6. At equilibrium, there are 2.5 mole of SO2, 1.35 exponent negative 5 mole of oxygen, and 8.7 mole of SO3, which is present in a 12-liter flask. Calculate the Kc, so means that it must be in the concentration at 700 degrees Celsius. So as the question before this, first we are asked to find the equilibrium constant. So in this question, they already give us the number of mole at equilibrium. Next, concentration means number of mole over volume. In the question here, they give us all in the unit of number of mole. So before we can get the value for the Kc, we need to calculate the concentration for each of the reactants and product here by using the formula number of mole divided with the volume. So for SO2 is 0.2083 molar, oxygen 1.125 exponent negative 6 molar, SO3 is 0.725 molar. Then next we are going to write the Kc expression at where it is going to product over reactant. So this is Kc expression. Then from the value over here, we substitute into the calculation step, and then end up we will get 1.077 exponent 7. There is no unit for the Kc expression. However, if you want to place the unit, you can, but just make sure you have to place the correct unit. For example, in this question, because we have 0.725 to the power of 2, so means that the concentration is m to the power of 2 over m squared multiplied with m. So m square and m square will be cancelled out. So the unit will be per molar. So if you want to place the unit, you make sure you place the unit correctly, which is per molar. Question 7. The partial pressure for PO3, O2, POCl3 at equilibrium are 5.05, 2.5, and 101 kilopascal respectively. Calculate the equilibrium constant Kp for the reaction. So again, all the pressure given here, refer that the reactants and product are at equilibrium. And then P stands for pressure. So that means we are going to substitute the value of pressure in the Kp expression. So because of the pressure given us here is in the kilopascal, so you may convert it to the ATM by divide with 101.325. So end up you will get 1.62 exponent 4. So again, Kp also has no unit. So beside from in terms of the ATM, basically you also can substitute the value of the partial pressure in the unit of kilopascal. There is no problem as well. So still the same Kp expression, but the value now you substitute in are different. So that's why your final answer for the Kp is 160. However, most of the time, we are encourage students to convert the unit of pressure to ATM. Tutorial question number 3. In an experiment, 1 mole of SO3 is introduced alone. So means that we only put in SO3 in a 2-liter container. And when the equilibrium is established, 0.152 mole of SO3, 0.414 mole of oxygen, and 0.848 mole of SO2 are present. So means that in the initially only SO3 is present. Okay, this one we consider initial. But at equilibrium, because as we already know, one of the characteristics for the dynamic equilibrium is the rate of reaction. Forward and backward are the same, means that at the same time both reactant and product are present. So that's why you can see all the reactants and all the products are present at equilibrium. So first we need to calculate the initial concentration for each reactant and also product. So like just now we mentioned, initially we only introduce along the SO3. So that's why the concentration for SO2 and O2 are equal to 0. But don't forget, given us the unit is mole and then also given us the volume. So by using the formula mole over volume, we will able to get the initial concentration for SO3 is 0.2, while for the SO2 and O2 is 0. Next one, calculate the concentration at equilibrium. So in this case now, we are going to calculate the concentration for SO3, which is equal to 0.076, and SO2 0.424 molar, and then the last oxygen is 0.207 molar. Question C, sketch the variation concentration of SO3, SO2, and O2 over the time on the same graph. Okay, so means that you only can draw or sketch a graph with all the 3 substances. The curves are in the graph. So this is how the graph looks like. We have the concentration, okay, versus the time. So initially we only have SO3, so that's why this is the concentration as we calculate just now in the question A, 0.5. So the concentration of SO3 will going to decrease until one level at where we already calculated just now is 0.076 molar. While for the SO2 and oxygen, they are going to increase. So that's why increase from the 0, because initially there are no any oxygen and SO2 are in the container. So now they also will increase up to one moment. The concentration will remain constant, which at the 0.207 and also 0.424 molar. So basically after that, okay, we have to draw one more line in this case. Okay, so and then here you will mention that achieve equilibrium. Okay, because once achieve equilibrium, the concentration will keep constant. Okay, so basically here, supposedly at here, you still need to increasing the concentration until here only we start to keep constant. Okay. Question D, calculate the Kc for the above reaction 473 Kelvin. So as we know, first we need to write down the Kc expression. Since in this system, all the reactants and products are in the gaseous phase, so all of them will be appear in the Kc expression. So after that, after we write the Kc expression, then do remember that we have to substitute the value given in the equilibrium, which is 6.443. So because of Kc is stand for equilibrium constant, so the concentration that you substitute over here is at equilibrium. Okay. Then question E, would Kc change if the reaction takes place at 573 Kelvin? So the answer is yes. The Kc is going to increase. Okay. So last question, calculate the Kc for the following reaction. So when we look at here, this reaction is happened at 473 Kelvin, which is quite similar with this one. The only thing is the reactant and the products now is at different position. At the above condition, SO2 and oxygen is the product, but now SO2 and oxygen are the reactant. So this means this Kc will equal to 1 over Kc above. So we will use 1 over 6.443 and then press the calculator. You will get the answer. So the answer is 0.1552. Tutorial question number 5. This is the Kc value 4.5 exponent negative 2 for this N2O4 to the NO2. So now we are given different chemical equation, but they are slightly similar with the equation given over here. Okay, so now we are going to calculate the Kc expression for each of the ABC. So first we look at the first equation, the Kc expression in the question given here. Kc is equal to concentration NO2 to the power of 2 over concentration N2O4. Okay, we didn't know the concentration at equilibrium because the question already calculate for us, which is 4.5 exponent negative 2. So then they asked us to look for the Kc for previous equation, which is 2NO2 produce 1 mole of N2O4. So because we are not given the concentration, so we cannot use the Kc expression as we tried to discuss in the previous question. So, but then we will notice that if I write the Kc for the equation A, it will be N2O4 over concentration of NO2 to the power of 2, which this is the reverse of Kc above here. So which we will mention equal to 1 over Kc. So when 1 over Kc, so I will press the calculator, 1 over 4.5 exponent negative 2, and then I will get the answer is 22.22. So this is the answer for question A. While for the B, we will notice that this equation is similar with the equation above here. The difference is the coefficients are different. So for equation B, the Kc expression will be concentration NO2 to the power of 1 over concentration N2O4 to the power of 1 over 2. So then if we look at here, the power 2 become 1, while the power 1 become half. So in this case, we know that this one is the Kc above with the power of 1 over 2. So the Kc given is 4.5 exponent negative 2. So with the power 1 over 2, so or it is actually square root of 4.5 exponent negative 2. So when you press the calculator, you will get the answer 0.212. The last one, C, is reverse for the equation B. So that's why we can just directly write down Kc for the C equation is equal to 1 over the Kc for the B equation. So 1 over 0.212. Press the calculator. We will get the answer is 4.717.
Question number 8. Calculate the Kc and also Kp for the following reaction. If 350 Kelvin and the equilibrium mixture contains 2.5 mole nitrogen, 3.5 mole oxygen, and 0.06 mole nitrogen dioxide in 2 liter Wenzel. Okay, so based on this question, it is very clear that the number of mole given in the question is at equilibrium. So we are going to use a Kp or Kc expression to solve this problem. This is our first impression. But then you will notice that at the same time, the question is asking us to look for the Kc and also Kp. So when this happens, you also need to know there is possibility that we are going to use the formula Kp equal to Kscrt delta N to solve it. So first, we have to solve the Kc expression first. So then we need to write down the Kc expression. So based on here, the Kc expression is nitrogen dioxide square over concentration nitrogen and then concentration of oxygen to the power of 2. But because of the number of mole given in this question, so we need to convert the number of mole into the concentration. So in this case, all this number of mole will going to divide by 2, okay, because the container of the volume of the container is 2 liter. Okay, so concentration NO2 is 0.06 divided by 2 will be 0.03 to the power of 2 over concentration nitrogen is 2.5 divided by 2 is 1.25 to the power of 1, while oxygen is 3.5 mole divided by 2 will be equal to 1.75 to the power of 2. So press the calculator, you will able to get the answer is 2.35 exponent negative 4. With the presence of Kc, so basically if you want to find the Kp value, okay, so it will be partial pressure NO2 to the power of 2, partial pressure nitrogen, and then partial pressure oxygen to the power of 2. So if we want to find the partial pressure, basically we can use the PV equal to nRT. Because from the question, we didn't know the pressure for each gas, but we know their volume, we know the number of mole, we know the value of R, and also know the value of temperature. But if you use this formula, this method to complete the question, you need to calculate the partial pressure for nitrogen dioxide, partial pressure for nitrogen, and also partial pressure for oxygen, which this is will take longer time. So if we want to make it simple, then we can use the formula like we mentioned just now, the Kp equal to Kc RT delta N. So Kc is already calculated over here, 2.35 exponent negative 4, and then we multiply with the R. In this case, we always use 0.08206, multiply with the temperature, which is 350, and then the delta N is mole of gas of product. Okay, delta N is equal to mole of gas product minus mole of gas reactant. So in this case, we have 2 mole of product gas, and then we minus 1 plus 2, so the answer will be negative 1. So here the delta N is negative 1. Press the calculator. We are going to get the answer, which is 8.182 exponent negative 6. Last question in this video, tutorial question number 9. So calculate the Kp and Kc for the reaction. So again, in one question we need to look for Kp and Kc expression. So it will be involve the formula Kp equal to Kc RT delta N. So in this case, because we are given the vapor pressure of water at 25 degrees Celsius is 23.8 torr. So for this case, we may start with the Kp expression. So we start like writing the Kp expression, which is partial pressure of H2O. And then this one we are not included in the Kp expression. So we can make it, because this one is given us in the torr is 23.8, so we can convert the 23.8 torr divided by 760, so that it will equal to 0.0313 atm. So the partial pressure for the water vapor is 0.0313, so it will be also similar as the Kp value. Then next we are going to use the formula Kp equal to Kc RT delta N. So this time we have the Kp value, but we didn't have the Kc value. R value we also have. T value, temperature is given. Make sure you convert it to Kelvin, so also given. And then the delta N in this case is, for the number of mole of gas over here is 1. Even though there is 1 mole of reactant, but this reactant is in the physical state of liquid, so the delta N basically is 1 minus 0. After you press the calculator, you supposedly will get the answer. Kc is equal to 1.28 exponent negative 3. Okay, these are the final answer for the tutorial question 1 until question number 9. So in next video, we are going to continue with the subtopic which involving more calculation, which have the ice table and also the reaction quotient. Thank you for watching this video.